Hello, everybody. This is Kenneth Wong, Senior Editor for DE. Welcome to a new episode of Hot Seat. This is a series where we put the latest trends and technologies under a microscope to see if they are solid and practical or if there are loopholes. So today we are talking about digital twins. So if this is your topic and you tuned in, stay with us. We have a lot more to say about that. Today's episode is sponsored by Hexagon, Rescale, and Siemens. All right. Before we start, a few housekeeping items. I want to remind everybody that if you have questions about the topic or questions for the panelists, you can type those questions in at any time. You can submit them into the Q&A box. We'll address as many of these questions as possible as time permits. For the ones that we cannot get to, I promise you we'll get back to you in writing with the help of our presenters. You can also download a PDF copy of today's topic and the related resources to the left of your resource window. If you are experiencing any technical problem, please visit our webcast help guide by clicking on the help question mark icon at the bottom of the console. If the slides are not advancing, you might want to try pressing F5 to refresh your browser. That usually resolves a lot of issues. Let's get into today's topic, shall we? Some say PLM, or Product Lifecycle Management, is the backbone of digital twins. Some say simulation is the key. Others say, no, live data streaming in from the field and edge devices are the lifeblood of a digital twin. So today, we're going to talk about what are the basic components that are necessary to build a hypothetical digital twin SDK, as it were. So let's meet the panelists, shall we? To start us off, we'll have Leo. Leo is from Hexagon. Leo, your self-introduction and opening remarks for 3 minutes, please.
Thank you, Kenneth. As Kenneth said, my name is Leo Kilfoy. I work in Southern California, and I work in the Hexagon's digital transformation team. We're focused at enabling customers to transition to digital applications and workflows that span design and engineering, manufacturing, and metrology. Our solutions are focused at capturing virtual and physical data and processes of products, manufacturing processes, and manufacturing operations. The goal is to help our customers make data-driven decisions based on digital twins, the data, and digital thread, the processes. Hexagon Manufacturing Intelligence Division supports companies in the discrete manufacturing sector, for example, automotive, aerospace, electronics, and medical devices. Our products span design and engineering software for physics-based simulation to model the real world, manufacturing software for CAM, MES, machine simulation and execution, and metrology software and hardware for assessing the quality and determining the as-manufactured product. Our metrology hardware devices include scanners, laser tracker, optical measuring equipment, high-precision coordinate measuring machines, and several other devices. We believe that metrology is one of the critical elements for determining the as-manufactured product of the digital twin. Today's topic is what's in a digital twin development toolkit. I'm going to call that the digital twin toolbox. Obviously, this is very relevant to the digital transformation team which I work. Today I'll be talking about 4 tools in the digital twin toolbox. I like to call them the 4 M's: model, make, measure, and monitor. And in a manufacturing context, this is design, production, inspection, and maintenance. All of these play a critical role in the digital twins and are all part of the digital twin toolbox. Let's start with a very basic question. What's a digital twin? A digital twin is a replica of an object such as a product, system, or machine. Large-scale digital twins can include factories, hospitals, and cities. The twin can take real-world data as inputs and produce predictions based on simulation and analytics to understand how physical objects behave over time. Hexagon is closing the gap between real and virtual. We believe the future of product development can only move at velocity by capturing the reality of what's being manufactured and assembled on the shop floor. Virtual tools have optimized many aspects of the design and manufacturing automation, but autonomy is enabled by validating the reality of what's happening on the product in the production line. Autonomy will help industry achieve the next level of quality, and productivity from concept to consumer. Our domain expertise in manufacturing and quality is now being put to work in the next generation solutions we are developing, connecting simulation and physical data in digital twins to optimize design and processes. That's it, Ken. Thank you. Back to you.
All right. Thank you very much. We'll hear more from you. For now, let's go to the next speaker. The next speaker is Peter. Peter represents Rescale. Peter, welcome. Your self-introduction and opening remarks for 3 minutes, please.
Thank you, Kenneth. Good morning and good afternoon, everyone. It's a pleasure to be with you and have this opportunity to talk about digital twin. My name is Peter Liu. I lead our solution architect and custom success team at Rescale. Now, for those of you who may not familiar with Rescale, Rescale is an intelligent computing platform for digital R&D. We're founded by two brilliant engineers with a mission to help engineers and scientists accelerate innovation through cloud computing and digital R&D. Now, being a computing platform, we work with partners such as the simulation vendors like MSC Software, Siemens, Ansys, Dassault, and many others, as well as the cloud infrastructure provider like Amazon Web Service, Microsoft Azure, Google, and Oracle, to provide a computing platform where our customers can easily deploy their simulation workflows and digital twin on public or private cloud. So I started my career in aerospace engineering when the concept of digital twin was just emerging. I witnessed the booming of the adoption of digital twin, partially fueled by the advancement of simulation software, such as a CFD solver that is able to capture the physical world with incredible accuracy, and partially fueled by the wider adoption of cloud and IoT devices at an industrial scale. We can all admit that we're seeing the term digital twin all over the place. It become this buzzword that we see in our email, white paper, and conference. While it's not too hard to come up with a digital twin model itself, it is still very, very challenging to deploy a successful digital twin solution that drive a business outcome, and as well as the infrastructure needed to support at that large scale. So I'm very excited to be on this panel today to really share some of the experience that we have working with our customers to develop and deploy digital solutions. We really believe cloud is a key enabler and accelerator to the digital twin adoption, and that help to build one of the part of the toolkit. So look forward to our panel discussion today, and back to you, Ken.
Thank you very much. Indeed, the term digital twin is becoming such a catchphrase that I worry that it might follow the fate of terms like PLM, where everybody define it the way they want it. Let's meet our other panelists, and that's Ravi. Ravi represents Siemens. Ravi, welcome. Your self-introduction and opening remarks for 3 minutes, please.
Thank you, Kenneth, and welcome everyone to who is listening to this broadcast. My name is Ravi Shankar, and I'm Director for Product Marketing for the SimCenter portfolio of simulation and test solutions within Siemens Digital Industries software. So one of the things I want to do is, as Leo did, start with our definition for the digital twin. And it's not that different from what Leo already talked about. We view this as a precise representation of a physical asset. The usage, we see it across the life cycle to predict and optimize performance. It can consist of multiple models. Importantly, it evolves and has a life cycle that must be managed. And it requires bidirectional connectivity between the physical asset and the virtual representation. Real-world performance data can be used to update the models, and simulations can be used to improve the asset performance. So I'll touch upon a couple of the slides briefly, and then use them also to elaborate further during the Q&A session and the discussion that follows. So one thing I want to point on this slide is that Siemens enables our customers to develop what we call comprehensive digital twins that span across the complete life cycle of design, realization of production, and the utilization. And they include representations for mechanical, electrical, software, and IoT systems. And there is both a feed-forward and feedback loop that needs to be built in that takes information and transfer them between these different phases of the product lifecycle. When we look at digital twins and the more advanced implementations of digital twins, we also see that there is this concept we are calling an executable digital twin. So we are working with customers on the creation of these executable digital twins, which are self-contained executable models that represent the behavior of an asset. These are real-time enabled through the use of artificial intelligence and model reduction methods, and are deployed on multiple types of platforms, including real-time platforms, edge devices, and of course on the cloud, as Peter pointed out in his opening remarks. The exciting thing about these executable digital twins is that their potential is immense. They can open up new and transformative business models, and that's really going to change, I think, engineering and the use of products tremendously in the future. For example, it allows equipment manufacturers to offer the usage of their products as a service and to continuously enhance performance. So that's certainly something new and exciting that's going to be true in the future. So if you're starting out on a digital twin journey, what should your investment priorities be? Based on our experience, we have identified 4 key dimensions that also correspond with the areas that Siemens is investing in to ensure state-of-the-art solutions for our customers. First, build the capabilities to model and capture the complexity of your product, all the way from material behavior to performance of entire systems. They should cover a broad range of physics, include both simulation and testing, since digital twin combines both models and data. Invest in intelligent design space exploration and emerging areas such as generative engineering that can transform innovation processes. Consider how you can speed up development through workflow automation, reduced auto models, cloud and AI enhancements that make your individuals, teams, and entire organizations go faster. And then finally, invest in solutions that enable you to build a digital thread that connects models, data, and people across all lifecycle stages. The underlying backbone that integrates all the data and twin information is indeed quite critical. I'll just spend a couple of minutes on one example of how a customer of ours is leveraging digital twins. Aker Solutions is helping their customers meet the world's energy needs with subsea systems. These subsea assets are subject to extreme operating conditions. The system must stay thermally insulated, and if for any reason the flow cools off, hydrate and wax start to form, and in deep water conditions, these can drastically impact productivity. So how do you guarantee thermal performance of a system that's 2,000 meters below the surface? That's where our solutions are helping Aker Solutions. They use SimCenter and their in-house expertise to develop and integrate fully digitalized assets, combining design and simulation models with real-time operating data. They call this the Thermal Insight Digital Twin, and it includes a cluster of 9 wells and delivers a prediction fidelity within 1 degree Celsius. So the advantages that they're seeing is operations based on real-time data, not on obsolete conservative procedures, reduced operational risk, increased uptime, optimized production and productivity, and higher overall asset profitability, unlocking the true value of this really expensive asset. With that, Kenneth, I'd like to thank you for the opportunity to participate in this panel discussion, and back to you.
Very good. This is contact information for Ravi, everybody, if you have specific questions for him. We are right on time. We are hitting the discussion point at 15 minutes into the hour, so that's exactly where we want to be. So let's start talking about the difference between the digital prototype versus the digital twin. To me, a CAD model, a detailed CAD model, maybe an assembly model, it may even have joint behaviors that you can manipulate to see rotating things are rotating and bolted things are bolted and things like that. But I would argue that it's not exactly a digital twin. So what makes a detailed CAD model a digital twin? What breathes life into a CAD model? Turn it into a digital twin. Leo, would you mind starting us off with that? Keep in mind, we can spend maybe about 2.5 minutes to 3 minutes for each question.
Yeah, perfect. Thank you, Ken. And great question. I agree with you. A CAD model is a representation of a product. It's an ideal representation. I like to say a nominal CAD model is always perfect. The assembly is always perfect. However, in the real world, parts and assemblies have variation due to a lot of factors, such as the manufacturing process and parameters, the wear of tooling, dies, cutters, material, environmental conditions during assembly, etc. All of those will change, could potentially affect the as-manufactured geometry of the digital twin. So one of the questions is, how do we go from the CAD to the real true representation of what that geometry is? So what I want to do is I want to look at an example and an automotive body assembly. So we have a SFX virtual assembly is a new solution that addresses digital twins of these kinds of assemblies. It uses a digital twin representation of the part and component, assembles those together, and then simulates the actual welding and joining process so that the final component assembly that is built, you understand the final shape. The product is being built on SFX. It's an engineering process backbone that connects design, simulation, manufacturing, metrology applications to provide a seamless, traceable workflow, i.e. the digital thread, and that connects the virtual and physical parts to the digital twin. How does this work? The solution uses Hexagon or other scanning equipment to precisely scan the real part. So this is the as-manufactured part. Next, the scan data and the CAD model the scan data is used to morph the CAD model into the as-manufactured shape. Now we have the actual digital twin of that part. Once all the parts of the assembly have been scanned, or a combination of those parts plus nominal CAD, we can virtually assemble these parts and simulate the clamping and welding processes to determine the deformation stresses and heat affected zones. All of these affect deformation. The solution allows us to simulate different welding techniques, welding sequences, parameters to create an optimized process. Just a real quick, what does it look like and how does it work? We start off with a workflow. You can either develop your own workflow or use one that's supplied. Once you have a workflow defined, you can execute that. It provides a guided step-by-step workflow maintaining the end-to-end traceability, which is very important. The first step of the process is to scan the part. That scan, as I mentioned, is we're going to be used to morph the CAD model geometry on the lower left here. And that gives us the as-manufactured part. Next, we can assemble those as-manufactured parts with the deviations that were from manufacturing to produce digital twins, and we also include the weld information so we understand how the welds are done. And then finally, we simulate the welding process, resulting in a digital twin of the assembly. That gives us the results of the deformation and the shape of the assembly. So there's just as an example of a digital twin process and how we go from CAD to a real part. Kenneth, back to you.
All right. Let me bring in then Ravi into the discussion. Ravi, what are your thoughts on that? Leo has talked about capturing the as-built situation and maybe even wear and tear that might happen over time. So what's your thought?
So Kenneth, thanks for this opportunity to kind of comment and give you my perspective. So I go back to this slide where we kind of defined what the digital twin is from our perspective. And it is true that CAD models can contain a lot more information than just shape, for instance. They can include FMEA information, for instance. They can also be the basis for simulation models, obviously. And the ability to tightly go or very seamlessly go from a changing CAD model to an updated simulation model is quite important. And of course, pre-CAD are also part of the digital twin. Data from the physical asset itself can augment with virtual sensors the performance of the digital twin. And remember that there can be multiple models associated with the digital twin, one for thermal performance, one for structural performance, electromagnetics, and so forth. So the key here is that the digital twin is not something that exists at one point in time for the entire development process. It's something that needs to continuously evolve, both before the physical asset actually exists, to help create that physical asset in the first place. And then as the physical asset itself goes through its own life cycle, the digital twin is also evolving. And to be able to track all of that and to manage it properly is a critical requirement. So I think that would be where I would emphasize our view of the digital twin. Kenneth?
All right, Peter, I want to turn to you. We're just talking about a CAD model. You really don't need a cloud infrastructure, but people talked about the need for a cloud for digital twin. Could you help us clarify that?
Yeah, absolutely. So, both my colleague here has brought up the definition of digital twin, which is a virtual representation of a physical asset or physical process. And I think one of the big misconceptions here, or a lot of people has, is implementing digital twin is just creating a virtual representation of that. But in fact, the limiting factor that many organizations face of deploying digital twin is not the development of the twin itself, but it's actually the deployment of the underlying infrastructure, the underlying resource needed to support a digital twin solution. So anything from the networking infrastructure to stream the sensor data, the IoT device from edge location to a hub, to maybe the HPC resource needed to simulate run the CFD finite element model to simulate the virtual model. So historically, we've seen that really only large organizations can afford deploy those expensive infrastructure to support a successful digital twin. I think the cloud infrastructure providers has really leveled the playing field. So let's take an example here. So let's say if you want to stream a sensor data from a diesel engine on a mining vehicle in Australia to feed into a digital twin model that you have running in an HPC data center in US. So it used to cost millions of dollars, right, to deploy such infrastructure, such network, to support those type of communication from one side of the world to the other side of the world. But now you can really piggyback onto the global infrastructure of the cloud provider. So let's say you can stream your diesel engine data, sensor data, working in that mine to the nearest edge location in Australia, then onto the backbone network of the cloud providers, and over to the digital twin, feeding to the digital twin model, let's say running on a cloud HPC platform. And that at a fraction of the cost. And oftentimes you can pay for just what you use based on the size of the data in megabytes or gigabytes, or the number of message being sent through that communication chain. So we see this really the upfront capital investment to deploy a successful digital twin is no longer required. So, and look, same thing with the computation side. So it used to be you have to build a data center and put millions of dollars of HPC equipment and servers to simulate that, to have the infrastructure to do the simulation. Now with cloud, you can run those at a pay as you go. Oftentimes, a couple of cents here and there per hour per core. So, I believe the role of cloud infrastructure is really the enabler to democratize digital twin for any organization of any size to implement it. And I think that's the direction of our industry is moving toward. Back to you, Ken.
All right. Now this time, I want to talk about the different types of digital twins involved. So I'm pretty sure that the digital twin of an engine block with this very specific serial number is very different from the digital twin of, shall we say, a process plant with moving assembly lines and peoples and equipment that are always in action. So are the requirements for each of these different types of digital twins different? Let's talk about that. Ravi, would you mind starting us off this time?
Yeah, sure thing, Kenneth. So, in our view, this whole concept of digital twin is actually equally applicable towards products and towards manufacturing plants. And I go back to this slide that I presented earlier. And there are a number of things that are going on in this slide. So first of all, for products, you can think of the domains of applicability to include design, manufacturing, and usage. And for a manufacturing plant, it similarly covers production development, manufacturing operations, and plant performance and maintenance. So there really are more similarities than differences over here. The digital twin of a plant itself may be comprised of a number of digital twins of individual systems. And the process of producing something can influence the digital twin of the product and the twin of the manufacturing process as well. Think of how, for instance, inadequate cooling of a 3D printer head can impact both the production speed, but also the structural performance of the part being printed. So this idea of digital twins of different systems that make up an even larger system is going to be something that's quite important in the future. And it's not just restricted to the manufacturing space, right? So even if you think about creating a digital twin, for instance, of a vehicle that's traveling down a road and interacting with systems that are traffic systems, or interacting with a digital twin of a different vehicle, being able to interact with each other, and for manufacturers to be able to simulate the performance of these different interactions prior to it actually being implemented in the real world. That really is the potential for digital twins. So I would say there are, my main answer would be there are more similarities than differences, but the complexity level certainly increases as you have more systems that need to interact with each other.
All right, Leo, would you mind chiming in as well? What would you say is the different components that are required for, say, the digital twin of an autonomous car as opposed to the digital twin of a smart plant?
Absolutely. So there are clear differences, and I agree with Ravi that there are clear differences, and there's also different inputs to digital twins. A digital twin of, if you consider a fleet of vehicles versus of identical vehicles, which aren't identical as we know, versus a living, breathing, ever-evolving factory are very different. Each of these have their challenges to manage the precise traceability across the twin, the life of the twin. For example, capturing data of a vehicle in the field can be difficult due to connectivity. Two vehicles of a fleet can be operated in different environments. That can lead to potential differences in things like maintenance schedule and things like that. Factories, on the other hand, often are singular. They're not a fleet. They're oftentimes unique. They also change over its life cycle. So the things that I put in the toolbox, the model, make, measure, and monitor, still apply in all these cases. For a factory, how do we use the digital twin? Just using a factory as an example, and in addition to the digital twin, there's the promise of Industry 4.0, which the IoT, the connectivity, to really do smarter manufacturing. That's one of the questions that customers are asking. Let me push this. Oops, sorry, slide. There we go. So what I want to do is talk a little bit about the manufacturing customers want, what do they want from the digital twin and Industry 4.0 solutions to support smarter manufacturing, and how can they, what type of information do they need to put in to capture? The first thing is compiling the data available in the factory. That's a very fundamental thing. So if I'm looking at a factory, how do I get that data into a place? Using the data to obtain insights into the design and manufacturing challenges and improve the quality and productivity, those are key elements that we want to be able to get out of our digital twin. Integrating the systems can help drive the decision-making processes that are going through the life cycle of that factory. And a lot of times with the digital twins, you want to crawl, walk, run. So you want to start with solve your immediate needs, but you want to be able to scale to the future needs. If we look at a factory and consider kind of some of the work that we're doing here with SFX, SFX targets the integration of the IT, the OT, and the simulation to inform the digital twin and create and optimize manufacturing processes. As Ravi said, there's different, with the digital twin, there's different inputs coming from a variety of different areas. You have asset digital twins, as an example, that are feeding this information. To optimize the manufacturing, you want to ensure that you are not only capturing the data from the assets, but also that you're capturing the production data as well. So contextualize the data is very important. Turn the information into actionable information. Digitize and enable company-wide BI so you can be looking at the data, and move the data from where it's created to where it provides value. So the traceability, simple things like shift summary reports or downtime tagging or production tracking are all important aspects. We look at there we go. Sorry about that. We look at the digital transformation as a progression, really kind of an evolution, trying to capture that information of the processes, then the activities and the operations, and involving them into digital twins to feed that. So all that information informing the digital twin so you can make those decisions. At SFX, we're doing a lot of, in Hexagon, we're doing a lot of things with the SFX platform to provide solutions that support these ideas. These are some of the examples of just a variety of different solutions that we are building to support digital twins for manufacturing operations and engineering. These are some of the examples listed. Wanted to kind of provide that as far as if, connected worker all the way through. So the idea of your operations, things like connected worker, AR monitoring, line walks, paperless traveler, digital quality, downtime tagging. And you get into things that are more engineering based, into virtual assembly, which I showed earlier, being able to do smart additive manufacturing. Those are some examples of how we're trying to build and put the tools for a factory, in this case, into a digital twin. Kenneth, thank you.
All right. Peter, let me ask you this question. Some people might be thinking, if we think about cloud, we can think about Amazon Web Services. So if I can simply today log on to Amazon Web Services and get the cloud instances that I need, why do I need Rescale? What is it that Rescale is bringing into the equation that makes it essential for digital twins?
That's a great question. So, all the cloud providers like AWS has come a long way when it comes to make it easy to use. Some even have developed very specific services tailored for digital twin. For example, Microsoft has developed a service called Azure Digital Twin. But if you look across the landscape of digital twin vendors and providers and services, it is still very fragmented. Every simulation or digital twin tools has its own unique way of installation, set it up, and deployment with a very particular data standard that they use. And every cloud provider has its own unique set of services. So they have their own API endpoints, how you work, how you spin up different services and interface with those. So it becomes quite a challenge to implement, just because that every digital twin deployment on the cloud will become highly customized and require very special skills and knowledge to operate and maintain. So that is the gap that we see that we can fill at Rescale. I remember when I first tried to learn Python 10 plus years ago, I really love Python, and because its ability to interface with other codes, actually, such as Fortran and C. So I was jokingly calling it the super glue to orchestrate and bring other existing codes and written in different languages all together. And that's the role I see Rescale platform play today in the space of digital twin. So we bring our software vendor partners like MSC, Hexagon, Siemens, and others together with the underlying cloud infrastructure partners of ours like Amazon, Azure, and others. So on our platform, we have all the different software tools preloaded and deployed across different cloud providers. And we offer that as a turnkey solution. So our customers can deploy digital twin models and simulations on any cloud providers, any kind of infrastructure, without the need to learn all those IT skills and knowledge that would require otherwise. And we try to fill that gap, and being the super glue in the digital twin solution, try to bring different components together through the Rescale platform as a service to offer to our customer base. Back to you, Ken.
All right. Now let's talk about the challenges of sustaining and maintaining a digital twin. I would argue that even if you can capture the wear and tear and the exact way in which a product is existing in the field, it still is a snapshot of that product in a point in time. It's not exactly giving you the diagnostic abilities unless you are able to recreate the behavior of a landing gear or a wind turbine blade or whatever that might be, so that you know in the future, predict when it might fail. So what are the challenges of recreating the real-world behavior of a field device? Leo, would you start us off?
Yeah, absolutely. Of course, Ken. Thank you. There's always challenges. There's always new challenges coming up. So when you design a product, at some point in the future, things are going to change, right? This is inevitable. So you need to be able to update. As I mentioned, the digital twin is a living, breathing object that needs to be updated. Sometimes this is driven by regulation that were not initially modeled when the product was made. The digital twin is will be continuously evolving. Many industries are also driven by, one of the desires of the digital twin is to get rid of, field inspections, but that's never going to happen because, of reasons for safety and other things along that lines. So many companies are driven by regulation, be it aircraft, rail, automotive, et cetera. So those are all industries that will require inspection. One of the things is, can we use those inspections, those regulations to feed the digital twin and use that information to drive better simulation? I'd like to actually walk through kind of a use case for you of that. And it's a company it's a Hexagon company. It's called NextSense. They do a bunch of sensors for steel, railway, and automotive. The steel, they're looking at the surface and profile measurements. The automotive, they're looking at flush and gap. But railway, which is what I wanted to focus at, they're looking at the wheels, brakes, and tracks. And I wanted to kind of drill into that because this is information that's happening in the field, a little bit related to your last question about field things that are serialized, as well as this question, how can we use that information, be it for simulation or analytics to determine the part after it's in service. Proper management of wheel wear is going to be driven by regulatory requirements for safety and life cycle cost. Each wheel and like brake of a train is tracked. So if you think, when we get out of COVID times, if you think about all the commuter trains that are out there, every wheel, every brake that's out there is inspected very frequently. One example is every 6 weeks, every 30,000 kilometers. If you think about that the next time you travel, that's pretty astounding. Look at the number of wheels that are on a train. Wheels are a massive cost driver for the railway industry. Wear varies based on many factors: load, mileage, weather, track. Many of the decisions about resurfacing or replacement of the wheels is based on experience, and several measurements are made on wheels and brakes. The measurements include, the front to back profile, the shape of the wheel, et cetera. Evaluation is based on kind of those critical dimensions. We look at So if I were designing, if I go back to the simulation question of can I simulate every use case, the answer is yes, we can simulate quite a few of the use cases, but there are always things that are going to happen in service that you want to be able to update that digital twin model. The state of the art, that information is not making it into the digital twin. The state of the art is really condition based. This is isolated information that's not being fed. It's really, kind of green, yellow, red kind of categorization. That information is tracked. Action, green is good, yellow is the information. Action may be required on the next inspection, and red is very simply requires immediate disposition, which can be expensive. And can include exchange of a wheel set or reprofiling the wheel. If we can make use of that information and start to update our models, our digital twins of those wheels, we could start to learn from that. And if you could start to connect that information to the cloud, now you can start to do things like enable predictive maintenance of the railway sets. This becomes really, really important when you start thinking about cost. Allow better planning of the maintenance. So now you can start using that information further downstream. You can optimize the lifecycle cost and the ideal asset utilization. If you think of something like a wheel, you can make sure that you're getting your full life out of the wheel. You can use that information to feed the simulation model to identify potential problems in the future. And by building a critical basis data so that it can update the simulation model. Things like the cost, the section profile over time and mileage. And then eventually you can support things like trends, topography of the shape, things like the effects of the train data, the weight, the mass of the vehicle, the speed of the vehicle, the track that it's running on to predict wheel life. Those are some of the things as far as that I believe are different is I can take my best, we can put everything we can into the simulation model initially, but we want to be able to update those simulation models and the digital twin models, more importantly, across the life cycle of the part that we're talking about. So, Kenneth, back to you.
All right, very good. Let me have Ravi chime in a little bit as well, and we're going to start to get into the Q&A very soon. So, Ravi, if you could maybe keep it tight, I'd appreciate it.
Okay, sounds good, Kenneth. So I think the question that you asked is actually quite important, and I'd like to go back to the 4 imperatives that I introduced earlier. The model is deliberately simple so that it's understandable, and we put this together to let people realize where the investment priorities need to be for the digital twin. So there are many challenges to capturing and influencing real-world behavior. It starts with creating the digital twin, which involves building the right models with the appropriate level of fidelity for each stage of the development process. These models should combine both simulation and test, since a digital twin does in fact need to deal with both types of data. Test data and real-world data is usually not clean, and so you need to develop expertise to extract the appropriate KPIs from this data so that they are actually usable within a development process. Sometimes real-world data is not easy to capture or measure, and in those instances, you need the ability to intelligently exercise the simulation models to capture edge cases. That's really the focus of exploring the possibilities, to really understand how you can make sure that the digital twin is helping you do better than you could without those digital twins. There is the challenge of converting models into executable digital twins, which are these real-time models, and that's where you need to develop expertise. And there are challenges with respect to AI and reduced order modeling so that you can have a significant way forward. And then staying integrated, making sure that every person, every model, all the data within the entire life cycle is actually connected. And this is happening across all the different disciplines that you need to take care of, because performance isn't limited to just one aspect. So yes, there are lots of challenges, but I would argue that there are very real solutions available today as well to help companies overcome these challenges. And then I would go back to these 4 items as our fundamental framework for thinking about those.
All right. Peter, I want to ask you about. Thank you. Peter, let me bring you into the loop as well. What would be the challenges in terms of the cloud infrastructure? Do you have any tips on how to set up correctly so that you can recreate the real-world behavior of the digital twin? And while Peter is answering, Ravi and Leo, I'd like to ask you to start looking at the questions that we have received from the audience and maybe identify the ones that you would like to address. Thank you, Peter.
Thanks, Ken. I think the biggest challenge to set up a great digital twin is one word: is data. So that, to be more elaborate a little bit more, it's data collection, data management, data governance, and data streaming, right? So, for example, let's say with a living plant, right? The data is constantly changing. So whether it's like the external environment, like the temperature or humidity, or the action and decision being taken by the plant operators, which is typically less predictable in nature. So you first have to have sufficient sensors, IoT devices, cameras, to be able to collect those data at a sufficient sampling rate. Once you collect the data, and each plant, for example, can potentially generate gigabyte, if not terabytes of data each hour. So, and a big portion of those data will need to be fed into the digital twin in almost real time to be able to do those predictions, diagnostics, quality controls, and things like that. And finally, it depends on the type of plant we're talking about. The data storage requirement may need to meet certain industry standard or compliance requirement. So, for example, you may be dealing with ITAR data, export control data, or you may have healthcare data with HIPAA. So the main message I want to give here is data play a really, really crucial role in planning, implementing a successful digital twin. You require a single source of truth to maintain that, and it often can be the main bottleneck for the quality and accuracy of the digital twin. So really make sure that you plan the data management and governance as key part of your digital twin strategy. And at Rescale, and we're trying to help bridge those things together. So I certainly encourage the audience here before jumping into the Q&A to give a try. So go to rescale.com, sign up for an account. Whether you're going to set up your MSC Nastran model as your digital twin or Siemens SIM centers, or whether you want to run on AWS, Azure, or other cloud providers, you can set up your digital twin on the cloud with just a few clicks, and we'd love to help you implement successful digital twin solutions. Back to you, Ken.
All right, with that, we are going into the Q&A. Peter, hang in there, and you might as well address one of the questions that is already in the queue, and that is how do you manage the specific requirements for each different countries or regions? For example, in Europe, you have to comply with GDPR, and in US, you have to comply with ITAR. So what about the cloud infrastructure? Could you address that?
Yeah, absolutely. At Rescale, we spend a lot of time working with compliance. We have a security and compliance team that working with each country's compliance standard and make sure our customers or help our customers meet the data governance requirements that they need. So, and this gets a little bit messy because every country has its own standard and requirements in US, GDPR, Europe, Asia, and different countries. The way we handle that is that we actually set up separate platforms in an isolated environment, depends on the compliance needs. So, for example, in US, we need to work with government agencies, entities that require export control. So we have a dedicated Rescale platform sits on top of ITAR compliant data centers. So that will be the Amazon GovCloud or Azure Gov environment to ensure that every data, every information feeding to that platform meet or exceed that particular compliance standard. And we also ourselves at Rescale went through the certification process, such as SOC 2, Type 2 compliance, HIPAA, and others, to ensure not only are the data itself in a compliant data center, but also the Rescale infrastructure, Rescale processes, and our company meet the requirements of those standards. So that our customers don't need to worry about those, so they can offload some of the compliance burden to Rescale while we help them meet all those requirements.
Very good, thank you. We have a lot of questions, so I would say that to get through as many of them as possible, panelists, to maybe keep the responses to about 1 to 1.5 minutes, please. Ravi, let's start with you. Is there any specific questions that you'd like to address that you've seen?
Yeah, so there is one question that's been posed about using real data for digital twins, and is there a need for simulation models, in that whole mix? And I'd like to kind of address that. And I'd like to address that by maybe taking a look at the executable digital twin approach that I'd talked about. So there's no doubt the real data is needed, but there are several advantages of combining physics and data to build digital twins. Physics-based models deliver better predictive capabilities, offer a better way to understand model limitations. Physics can be thought of as a way to really condense data in some ways. The use of simulation models also allows us to augment real sensor data with virtual sensors to improve insights. I mentioned edge cases before. These are conditions that are rare, but could potentially be catastrophic. And they are very difficult if one is looking at only real data to kind of capture everything that's going on with edge cases. And that's where I think having a digital twin that's also based on a simulation model can be used to exercise and discover all these edge cases and build a much better digital twin. But of course, real data is also needed, right? I think Leo maybe pointed to this, that simulation cannot capture everything to the fidelity that's required. And that's where real data can step in and fill some of those gaps. So we strongly believe that the combination of physics-based simulation models and data is really the best way to realize digital twins. Hopefully that kind of answers this question, yeah.
I think that's a pretty good response. Leo, any questions you'd like to address, sir?
Yeah, actually, there's one that was, I think, came in during the presentation I was giving, or answering a question regarding, it says, does the digital twin require or mandate a non-nominal CAD representation? And the answer is really kind of, it depends on the use case, and I hate to give you an answer, no answer. I apologize for this. Does geometry, in the case I was giving you, geometry clearly plays an important part for assembly. For if I'm looking at how I assemble parts together, if I have variation, whether it be, and I'll give you an example of a sheet metal that I'm bringing together to build a door, which was kind of the images that I had there, or if it's the leading edge of a wing on an aircraft, and it's composites, obviously understanding the as manufactured part can be very critical because it can build distresses, change life, those things. There's other things, though, that can also, and you may have use cases where the geometry is less important, but other factors like the things like the behavior of how it responds, how a product responds, where CAD may or may not be important. Generally, CAD is important to some degree, but whether you need the nominal CAD is sufficient or not is going to be use case dependent.
Peter, this question might be relevant to you. Somebody asked, how do you implement data reduction strategies to make certain high sampling rate IoT sensor data? Since I think what they're trying to get at is if you get a whole large 1 gigabyte data sets of, say, temperature readings every minute from your field device, how do you make it manageable? Do you have any suggestions for that sort of situation?
Yeah, I think the technique depends on the type of digital twin we're talking about. So there's a lot of tools out there and algorithms for reduced auto modeling as example, or try to work with the data at a reduced sampling rate. Because in the end of the day, the bottleneck can often be just the pipe, how wide the pipe is to feed the data from one location to the other. And there's our compression algorithm that you can leverage to compress the data ahead of time. Or to desample, reduce the sampling rate on the data source. So, and there's intelligent algorithm based on the kind of AI concept where we can reconstruct the data with a reduced sampling rate. So you still achieve the high sampling rate of high fidelity while you don't need to have a wide pipe to feed those data. So maybe I don't know if it's that exactly what the question is referring to, but there's a lot of technique out there try to do reduced sampling rate data, reduce auto modeling to feed those data.
All right, very good. Ravi and Leo, I want to
Kenneth, maybe if I can jump in on that
Please,
topic as well, right? I think that's exactly right. What Peter was saying. And I think there is a lot of expertise built into organizations such as Siemens, where we have been working with test data for a long, long time, right? So we understand there is expertise built into how to take test data, which is not only, I think, very large in volume, but also very, I'll call it dirty data, right? There's a lot of signals that need to be cleaned in order for the true information to be extracted. And leveraging that expertise and being able to do it both on edge devices and then transmitting to the cloud only the data that's needed to be transmitted, I think is where companies can benefit in terms of using this data reduction.
All right, very good. Ravi and Leo, let's do this. Let's have each of you take one more question, and then I'd like to see if I can give you each a chance to do closing remarks. So let's start with you, Ravi. What question would you like to address?
Right. I think there was a question on data management, and the question is, isn't data management the big issue? If the twin is real time, is there a black box where I can see the state at some previous time? Where is that data kept? And I think it also relates to another question which had to do with ownership. So for sure, hopefully through my presentation, it's been clear that we do believe that data management is a critical piece of the equation. It's not only a data management problem, but data management is critical, and it's critical from two different aspects. One is the evolution of the digital twin all the way from the early concept till it's actually in use. And then there is the data associated with capturing, I think, the data of during usage and being able to feed that back into everyone who really needs that data in order to make the next level of information. So yes, data is critical. And I would say that the black box comment relates to the ownership. Who exactly owns the digital twin? Who owns the data behind the digital twin? Who can control where the data should go? I think is going to be an individual decision that needs to be made by each company in terms of the IP that they need to protect. And then I think it opens up many, many new different types of business models for companies to step in and provide value, because you're no longer just creating an asset that you sell. You're having to be involved in the maintenance and all kinds of other activities associated with that asset.
All right, very good. Leo, one more question that you'd like to take?
Yeah, I was actually going to follow on to what Ravi said. I agree with Ravi. I was going to say the other thing that I think the question that was asked is about the volume of data. So if you think about different systems, whether it's a factory or it's an aircraft or something like that, it's a tidal wave of data coming in that needs to be managed across the life, and some of these lives may be 30 years in being. So that's where a model can actually help you can use the data to build a model to understand particular aspects as part of the digital twin, as far as its behavior, whether it's an aircraft flying or and understand potentially use that data to drive and hopefully reduce some of that data. So persistence, how long do I keep the data? How do I use the data? As Ravi said, some of the data coming in is going to be all over the place because of how it's brought in. So you want to be able to bring that data and make it available, make it so it has context. I think that's a big issue that from a data, and I don't think all of that's solved today. I don't think there's a quick answer to that. I do think if you start looking at a life of an aircraft as an example, and the amount of data that you get from that on a daily basis that it's flying is an immense amount of volume. I've seen some stats on the numbers, and it's huge. And looking at that across 30 years becomes very interesting. So those are some of the challenges that are still out there.
Very good. Gentlemen, I'm sorry, I won't be able to give you a chance to wrap up because we're actually hitting the 1 hour point. But our webcast producer, Steve, is going to start displaying some of the resources that we have assembled for the audience that are related to today's topic. In the meantime, I want to thank you, audience, for spending your precious time with us. And I'd also like to thank Hexagon, Rescale, and Siemens for making this live discussion possible. I want to thank my panelists for addressing all the questions that I cannot possibly address on my own and sharing your insights. Until next episode, this is Kenneth for Digital Engineering saying thank you, everybody, and we are out.
Thank you all.
Thank you.
Bye-bye. Thank you.